Flashback time. Okay, so what we're going to do here is we're going to flash back to what you might have done last year. I know my classes did this at the very end of last year, but we're going to flash back to gravity. And by thinking about gravity, we'll actually be able to think about electrostatics in a very interesting way and get us a lot farther ahead. So last year, when you were thinking about gravity, when you're thinking about planets and the force of gravity changing as you move further away from an object, without the calculus, we can at least say that F equals big G, which is our universal gravitational constant, times m1 times m2, so that's gmm, over, and if you guessed it, it is r squared. Okay, it's important for us to note here that G is a fundamental constant. And what we mean by a fundamental constant is that value of G simply exists because here on Earth, we chose meters and seconds and kilograms to be our units of measurement. And whenever scientists started plotting things for this GMM over r squared, a constant appeared in the front of it, which happened to be this G, and it happened to be a certain number simply because of the units we chose. If we were on a different planet, a different world, or a different species that evolved, and we chose different units of measurement, that G would have a different value simply because our units changed and it needed to exist in order to fit the graph. Okay, so it's just a constant, but it's a fundamental constant of nature. The two other things we have are mass for M1 and M2, and these are intrinsic properties. And because these are intrinsic properties, they are simply properties of nature. Mass is a property of nature. It is something that is physically there. It is something that is not changeable. It doesn't matter what my units of measurement are in. Mass is mass. Whether you're measuring that in stones or kilograms, like mass is mass. Okay. And last but not least, we have this value r in the denominator, which we are squaring, and r represents a radial distance. It represents how far away you are from the center of mass of some point. And if you recall last year, whenever we were doing these types of problems, we'd say, if here's the Earth and you are out at some point in space and we want to know the force due to gravity, we won't just take from the surface of the Earth out. We go all the way from the center of the Earth out to the point. So you'll need the radius of the Earth plus the altitude distance. It's that full distance that we need radially from that center of the object. Okay? So that's what we saw last year. F equals gmm over r squared. And there are some interesting things that come about due to this equation. We see here that if we take just two objects and keep them constant, this entire numerator, G being a fundamental constant and M1 and M2 being constants for your two objects, maybe that's you and the Earth or the moon and the Earth or the Earth and the sun, whatever, we see that the force acting on the object is proportional, so there's my little fish symbol for proportionality, it's proportional to 1 over r squared. And we call this an inverse square law. Inverse being 1 over and square being r to the square. This inverse square law pops up a ton in the world of physics. It pops up for gravity. We're going to see it pop up in a second for electrostatics. It pops up for magnetic fields. It pops up for sound. It pops up for light intensity and for sound intensity, just to clarify that. So it pops up a lot. It's actually a property of the fact that we exist in a spatial 3D universe. At least that's how we perceive it. And I say spatially because temporally we have time, and that makes our universe 4D and whatnot as we perceive it. But this inverse square law is kind of a big deal in physics. And if we wanted to just kind of plot this inverse square law, we could pretty easily. If we have, here's our force and here's our radial distance, we know this inverse square law is going to die off like that. So it's never going to actually reach zero. It's just going to eventually be 1 over a very, very large number, which isn't zero, but is very close to it. So we're never actually going to get a force of zero. These forces extend out to infinity, and that's what we learned last year. We're going to see the same with electrostatics. We know that this kind of equation works here because if we take a look at some just standard things from last year, let's take a look at this equation, but kind of rewritten in a slight way. So let's just take this equation, F equals GMM over R squared, and let me I want to get more space here. Okay, we'll figure out a way to do that. There we go. Okay, so if we take the equation, F equals GMM over R squared, we could set this up for two objects, okay? Let's say one object is the Earth, and one object is you here on the Earth, okay? If we set this up, we could say F equals G, which, if you recall, G has a value of 6.67 times 10 to the negative 11th, and units there are of newtons meters squared per kilogram squared. I'm going to kind of ignore units as I go throughout this because I know what my final thing will be. And then the mass of the Earth is approximately 5.9 times 10 to the 24th kilograms. And then there's the mass of you. I don't know what your mass is, so let's just call you M2 for now, make life a little easy. And then we'll divide this by the radius of Earth, because we'll say that you're just standing on the planet, which is approximately 6.38 times 10 to the 6th meters. Don't forget the square, okay? So that's what we have right now, just in terms of the force acting here, okay? Now, instead of looking at the force, let's look at something a little different here. Let's divide M2, your mass, over to the other side. So we'll wipe M2, and we'll bring M2 over here, okay? So what we have now is we have a force per some amount of mass. And because that could be your mass, and when I say you, I mean whoever is watching this video. Like, there's many people watching this video, right? Let's call this a unit mass. Let's just say it is some amount of kilograms. So the force per some amount of kilograms is equal to, well, 6.67 times 10 to the negative 11th times 5.9 times 10 to the 24 divided by 6.38 times 10 to the 6th squared. And when you run that, and be careful about the squared, you don't want to forget it, when you run that, you get a value of about 9.66 meters per second squared. And if we look at this here, there's a few things we should recognize, especially given what we know from last year. Meters per second squared, that's an acceleration. And 9.66, well, that's really close to 9.81. This is just gravity. That's the acceleration due to gravity there, okay? It is an important thing to recognize that the acceleration due to gravity here on Earth, that 9.81, that, while it is an acceleration, that is a force per unit mass. So for every kilogram that you have there, there's more force pulling on an object. And the reason why we got 9.66 here instead of 9.81 was simply because we took average values of Earth. Earth is not a perfectly spherical object. It's an oblate spheroid, and it's not uniform density throughout. There's veins of gold and iron and all sorts of like rocks and stuff in Earth, so it kind of gets weird on distributions, and on average we just use the 9.81, but here is a slightly different number, okay? So this force per unit mass gives us gravity, which we thought of as an acceleration. Now we're going to take this idea of a force per unit mass and we're going to carry it over to electrostatics. If we carry this over to electrostatics, let's take the same initial equation we had up here. F equals GMM over R squared, but let's this time put in a new fundamental constants, new intrinsic properties, and then see what's going on with radial distance. So if we do this, we can say that some amount of force is going to equal an intrinsic property. And for right now, let's just put as a intrinsic, not an intrinsic property, a fundamental constant. Let's just put a K for a fundamental constant, okay? So this right here is a fundamental constant. It's something that exists in order to fit a graph, and simply because we use units of, well, for charges, coulombs. Well, charge, that's like a thing electrons or protons have. It's intrinsic to them existing. So instead of saying M1, M2 for masses, let's say Q1, Q2 for charges. And if we have something like an electron and a proton, and we would like to figure out the amount of force, attracting them or repelling them. In this case, it would be attraction, opposite attract. Well, in this case, I need to know the radial distance they are away. So we're actually going to keep this r squared value, and it's squared due to the geometries of our 3D world. So this is what we have here. Instead of f equals gmm over r squared, we have f equals kqq over r squared. And if we now take one of these charges and move it to the other side, what we would have is F over Q. And that would equal KQ1 over R squared. But a force per unit charge is also equal to an electric field. We can think of an electric field acting as an accelerating field. We can essentially think of it as an acceleration there. It is what is causing our electrons and protons to accelerate. Just as a gravitational field, if you have an object, will cause objects to accelerate in the direction of that field. So that is a field that we are talking about. It's a force per unit charge. So in our last video, we saw force per unit charge equaling electric fields. That electric field also is equal to kq over r squared, where k is some fundamental constant, which we'll talk about in a second. Q is the charge that is creating the field. This is the charge that is creating the field. Okay? It's not the charge in the field. That's this sucker right here. The Q in the electric field equation is creating the field itself. Okay? Now the other equation we've got here from that we use to derive the electric field equation, F equals KQQ over R squared. This is a super important equation. This is what we actually call Coulomb's law. That is this equation right here. Super important. Oops. You need to have that sucker memorized and down pat, because if you know Coulomb's law, you can get electric fields off of that, and you can do pretty much everything you want within our electrostatics unit. Okay? Note, these are force vectors and electric field vectors here, and because of that, in some of our examples, we're going to see things get a little bit complicated here. Okay? Now I said I'd share with you what the fundamental constant of K is. K is a little bit weird to think about in terms of fundamental constants. So let's generate a little bit more space so we can scroll this down. I would like to scroll this down. We'll just scroll over. K is a fundamental constant for our charges, and we define K as equaling, this will be weird, 1 over 4 pi epsilon naught. And this equals approximately 9.0 times 10 to the 9th newtons meters squared per Coulomb squared. Now if you're looking at this and you're like, yo bots, what the heck is epsilon naught? Well, epsilon naught is the permeability of free space for an electric field. And I know that doesn't make a lot of sense right now. As we get further into the year, it will make a little bit more sense here because we got to draw electric fields there. But in reality, we're pretty much going to use just K whenever we're doing stuff for the AP2 class. We won't really use 1 over 4 pi epsilon naught unless you're doing stuff for AP Physics C, because we'll start seeing that some of the 4s and pi's cancel out and it makes life a little bit easier. Okay, but for right now, we don't need to do anything there. The only last thing I'd like to comment on here before I let you go is there are some fundamental differences in terms of how we think about Coulomb's law and the forces between charges versus gravity. Gravity is always an attractive force. Gravity will never repel anything. But as I kind of alluded to when I was talking about positive and negative charges, we can repel or we can attract objects that are positively and negatively charged. It's important for us to remember that like charges will repel. So if you have a proton and a proton, those are going to push each other away. If you have an electron and an electron, they're going to push each other away. But opposites, proton and electron, they're going to attract. This is especially important because what you'll find is that whenever you're solving for the force between objects, if you have a force which is a negative number, then these are going to be attracting one another because your Q values here are positive and negative. A positive times negative gives you a negative. These are attracting objects. If your forces are a positive number, they're going to repel, okay? And that's an important thing to keep in mind there. Whenever we start adding forces together, what I'll recommend, and I'll definitely recommend this in later videos, is even if you have positive and negative numbers and you're like, oh, I know what they mean, drawing a picture is super helpful because whenever we're looking for net forces on objects, we'll be able to say, hey, look, if here is a electron and here's an electron and up here is a proton, well, I know this electron is going to be attracted here and repelled here, which means my net forces when I add these together will kind of move upwards into the left by some amount, okay? It's very easy to kind of mess that up, especially if you're like, oh, this is a larger positive number than the negative number. Maybe it'll come to the right. You just got to be careful. We'll talk about that when we get to there. But for right now, just kind of know drawing pictures and having a good idea of that is a helpful thing, okay? So that's our flashback through gravity. Hope that was helpful for you. And relating that into electrostatics for Coulomb's law and getting an electric field equation. Don't forget what K is, 9.0 times 10 to the 9th newtons meters squared per Coulomb squared. And in our next video, we'll talk about some elementary charges and my favorite character from Ratchet and Clank, Captain Quark. Till next time, adios, take it easy.